In this brief introductory video, I'll explain how to use the Asteroid Institute's Impact Probability Service to compute impact probabilities and risk corridors for near-Earth asteroids. This tool can be used to validate and visualize what the agencies are already computing as impact risks for these objects, as well as in the future will allow users to run custom orbits through and detect impacts on them. To access Atom Impact Probability, go to b612.ai and click on it in the Atom Platform dropdown. This will bring up the main form. To start, you'll need to specify the orbit that you want to analyze. First, you'll validate that we can pull a state vector for the orbit you specified. Then you'll set the impact search parameters and start the job. We provide a tool to get orbits from 3 sources, which can be selected via this dropdown. First is the JPL Small Bodies database. This is probably the most flexible option. You can search by IAU number, designation, name, or SPK ID. The European Space Agency's NEOCP is similar to JPL, but orbits and therefore results may differ slightly. Scout, or the NEOCP, also from JPL, is more effective for recently discovered, unconfirmed, and actively studied objects of risk. Because these objects are not discovered, they must be searched for by their Scout IDs. You won't find these objects in other orbit sources. Finally, we will provide support for a custom orbits file, but if you would like to run your own orbits, please contact us to request access. After making your selection, in this case we'll choose JPL, type the requested designation into the search field and hit Find Object. If your object is found, you'll see a success message and can go on the rest of the form. For here, we'll try 2020 BV. And you can see we found our object. Keep in mind that you may have to try one or more variations on a designation in order for it to validate. For example, SBDB queries can be sensitive to spaces between the 2 parts of a provisional designation. Next, you'll be asked to pick a range of dates between which to search for impacts, which can be specified either by their dates or by the modified Julian date. At this time, this is limited to going out to 2099 and to a maximum of 100 years. We'll just use the default values for now. Now you have a choice. By default, we pick 10,000 Monte Carlo samples from the orbit covariance matrix and run each of those variants through the time range specified. But we also give you the option to run just the nominal orbit and bypass the Monte Carlo step. This can be useful to check whether the center of the covariance and uncertainty impacts, and it does run a good bit faster. For now, we'll pick the 10,000 draw option. Finally, we support impact detections with respect to the Earth and to the Moon. Pick one or both of these and hit the Run Impact Analysis button. On submission, you'll be taken to a loading page with some information on the submitted job. As the run progresses, you'll see status updates. This page will periodically check for updates and redirect to the results page when they're ready. A typical result run can take 5 to 20 minutes, although may take longer depending on the number of close approaches and the time span chosen. You can save or bookmark this page and come back later. The job will continue running even if you close your browser. Okay, so we've waited about 20 minutes and we've gotten our results in. I'm going to give you a quick overview about what you're seeing here and how to make sense of these results. First, there's an overview of the job definition that you set in the form. We also link out to the object in whatever service, SBDB, NEOCP, or Scout you use to get the state vector. Next, you'll see that we report whole run statistics. So, over the time range you specified, what is the total cumulative impact probability? Here, 0.15%, so 15 out of 10,000 variants impacted at some point during the time range specified. And also, what's the highest probability of impact for a single event? We call these unique impact events impact clusters. And these usually coincide with a particular close approach of the object to the Earth or the Moon. In this case, that maximum cluster probability was 0.04% or 4 variants. Below the whole run statistics are a list of those impact clusters. So as you can see here, there are a few different potential impact dates, the highest probability of which are in 2050 and 2056. If you click on one of these, 2 plots below will be generated. The first plot shows the risk corridor on the Earth. If you hit play, you'll see a procession of dots appear on the Earth. These are individual impact events simulated from the 10,000 draws and their potential point of impact. Now, this isn't the time for alarm. As you can see, there are only a handful of dots here out of the 10,000 samples simulated. In the next figure, you can see the full spread of those variants. So going to the second plot, here we see a simulation at the time of this impact cluster. And if we hit play, you'll be able to see the time of impact. Red dots here represent impacting variants, while blue dots represent orbital variants that don't impact during this impact cluster. The orange dot, which we'll have to zoom out a little bit to see, represents the best fit orbit at this time. As you can see, we've propagated out all the way to 2050, and the covariance of this object has gotten quite large, and we're extending out over a good range of its orbit. For our second example here, I'll show the results for 2024 YR4. Now, this object got a lot of attention in early 2025. It seemed like there was going to be a significant chance of an Earth impact in 2032, but as additional observations were taken, it became clear that that was unlikely. Now, we get about a 4% impact probability with the Moon on that date in 2032. As you can see here, we don't actually plot the risk corridor plots for lunar impacts, but we still plot the impact simulation, and you can see what that looks like here. Interestingly, the best fit orbit is actually quite close to the Moon in this case, so it'll be quite interesting to see what happens over the next opportunities for observations of this object. Now, it's important to note that many objects will not have any impacts, Earth or Moon, and that's to be expected. In this case, Bennu's nearest impacting event is about 150 years out, and so the time range specified here just isn't sufficient for that. It's also possible that the 10,000 Monte Carlo samples isn't enough to get sufficient granularity to detect impacts for a particular object or a particular impact event. We can support running more samples than this, but please reach out to us if you would like to run with more than 10,000 samples. Finally, the last thing I'd like to touch on is data availability. So for any run, we do provide access to all of the raw data generated, and that's the collision events, the Monte Carlo orbit variance, the initial orbit, the cumulative impact probabilities, and the impact probabilities for specific clusters. Each of these files are downloaded as Parquet files. They use the Atom Core library, which relies on the Quiver library, which was also developed by the Asteroid Institute. Now, each of these projects is open source. We link out to the documentation, and you should find them relatively easy to use. I hope this has been helpful to explain how to use Atom's impact probability tools. We plan to add additional features to this over the next several months, but if you would like to use this in greater depth, either with a larger number of objects or with a larger number of Monte Carlo variants, then please do reach out to us. We'd be happy to assist you. Thanks so much.